Okay, so we have this paradigm in computing. We have a couple different, let's say, broad ways of solving problems. And this one is simply referred to as input, compute, output, which is pretty much the way pretty much every program works, but it's kind of the model, right, of how you organize things, which is you ask the user for their input and you get it. Then you take that user's input and you do some computation, and then you output what you computed, okay? So we see this this is probably most directly done in your second lab with the third part, which is the Celsius to Fahrenheit converter. You ask the user for a temperature in Celsius, and then you run it through an equation, right? One that you've probably done before on a calculator, and then you output that answer to the user by printing it, okay? So there we go. So that's what we're going to be doing today. A lot of that just for some really big problems. So let's go ahead. So there's two big things to learn here besides just that method of doing problems. Making and documenting some simplifying assumptions. In other words, when we work on problems, it's good to either ask questions about it, or if you aren't being provided answers to those questions, then to make some assumptions and write those assumptions down so that we know what the logic is. And then, let's see, solving a problem by generalizing from a simpler version of the problem, okay? So these are kind of the three tasks. This first one is our first task, which is a conversion task. And we'll be doing this first, and then we will later on be tackling the other two. But this one's probably the most important, this first one, simply because it's so analogous to what's in your homework. So this one is a program that, well, we'll go through it, but we run it. It asks for a number of years. It says, enter the number of years. I'll tell you how many minutes that is. All right, let's see. 3 years is 1,576,800 minutes. Okay? So let's go ahead and run through this program and see how this works before we try to play with it for a bit. So first line is years is equal to input, enter a number of years, and I'll tell you how many minutes that is. So the input statement works a lot like a print statement in the sense that it can print something out, but it does a bit more, which is that once you once you hit an input statement, everything stops, right? Over here, you run it and suddenly everything stops. The computer is waiting for you to enter some information, right? So I'll put in 53 and it will then run through the rest of the program. On idle, it will just simply stop in the output window and wait for you to enter in something there, right? Essentially, it's engaging in some dialogue, right? And here, because of the way a web browser works, it gives us a dialog box to enter it in, okay? So that's our first thing. The second thing to do is years is equal to int years. Now remember, for lines 1 and 2, the way an equal sign works, it's the assignment operator. You take the thing on the right and you put it on the left. And I always have to remember to do this is your right and your left, because not mine. All right, so input, a number of years, and I'll tell you how many minutes that is. So when you do an input, it's asking the user to enter a string. Doesn't matter what you put in. If you put in numbers, it's still a string. A string can be any series of, let's call them glyphs, because letter does not fully encompass the sheer madness of what you can input into here. Right? Now, all emojis pretty much are just text at the end of the day. And we can see that in action right over here, right? You can paste it into a text box. It's something we'll learn later called Unicode, and I say learn, and I'm just going to like briefly gesture at it in the vaguest possible manner because it's actually it's actually a lot. But this is a string. You can input it. And we get an error. Invalid literal for int in base 10, happy face on line 2. Oh, I love that. If I put in apple here, I'm going to get an error. And if I put in 12 or 13, it will work just fine. Why? It all comes down to line 2. Line 1 takes in a string. Line 2 says we're going to do something with that string, right? We take in a string on line 1 and we store it in years. Then in line 2, we have this new function here, which normally I would have mentioned on Tuesday, and I just didn't get around to it. We have this function called int over here. Int is short for integer. You take whatever you toss into int, and it gets converted into an integer, right? So anything that can possibly be converted into an integer, it will. So here, when I'm entering in the letters 57, it takes the letters 57 and converts it into the number 57. Make sense to everybody? Because otherwise, now why do I have to do that? Because then I'm going to try to do multiplication, and let's see how well that works out. So years is equal to years, whatever. That's a nothing statement, right? 4 times 365. But remember, it's not the number 4, it's the letter 4, the glyph 4, right? The symbol for 4 times 365, which means you need 365 of them. And then, okay, and then we do 24 of those, and then we do 60 more of those. So it's a very long answer, as you can see. Okay. So data types do matter here, and oftentimes you'll just do this right after. Whenever you're taking in numerical inputs, you're probably going to do this right after. And just to answer that question that some of you may be having, the least surprising option, again, there is a float operation to turn something into a float. You just stick whatever you want to turn into a floating point number into the parentheses. And similarly, if you want to turn something into a string, you don't type string because we're lazy. We do str. We do str to turn it into a string. Okay. So anyway, so here let's go through here. So the problem so now we've got a number. We've taken the years, we've turned it into a number. And our goal now is to turn this into the number of minutes. So let's go ahead and go back to here, right? And remember, whenever we kind of do stuff, we can always rewind in here, which is always useful. Days is equal to years times 365. So right, there's 365 days in a year. So what this is doing, line 3 is doing, is saying, take the number of years. If it's 1 year, we'll multiply that by 365, and we'll get 365 days. If we have 2 years, it will be 730, I believe. Yeah, 730 days, and so on and so forth, right? But it will be however many days it takes, right? However many days a year is times the number of years. Then we can convert those years into, those years into days. Those days get multiplied by 24. Why? Because there's 24 hours in a day. Really odd number to decide for how many hours in a day, not 20 or not even 10, right? Those seem like nice. It's a multiple of 12. There's probably some reason behind it. Oh, and 60 minutes in an hour. That's weird, too. Why do we have 60 minutes in an hour and not 100? Okay. Days times 24 to get the number of hours. Hours times 60 to get the number of minutes. And that's how our conversion goes. So what would I have to do to turn this into a program that, given the number of years, turns it into the number of seconds, right? How would we go about changing that? Take a minute for yourself and go through the program and see if you can't make the changes, right? It's adding one line between line 5 and line 6, and then making a couple other things, but most of that work is making one line of changes. Oh, and I should mention this is not in any way, shape, or form a quiz. I give you the answer right afterwards. Just hopefully some of you have tried something out, but I know that was a very short amount of time, but I want to make sure we have plenty of time for other stuff. But I'll show you, right? Most of you probably did this, and this is correct, which is to do this and say, I need the number of seconds, right? Second, so I'm going to create a variable for it to hold the number of seconds, and I'm going to set it equal to something. Minutes, and I know this one, they are 60 seconds in a minute. So I multiply the number of minutes by 60, right? That math makes sense to everybody, right? We're multiplying from when we go from a bigger unit to a smaller unit, we have to multiply to get to a bigger number because there's going to be more of that smaller unit. Okay? And then, if you're like me, you're going to be overexcited and you're going to hit the save and run button. And you're going to put in 4 years is equal to 2 million or so minutes, right? Because we added this line of code, but then we didn't proceed to do anything with it. This is a very common mistake. You will make this for the rest of your life. So if you did that and you couldn't figure out why it was working, don't feel bad. You will do this forever. I do this all the time. So first off, let's go ahead and change the input to say, we're going to update that input with reality. Make it change to how many seconds that is. Then, print out. Years is, and then we change the variable we print out over here from minutes to seconds. And over here what we're doing is that we have this print statement with multiple commas to say there's multiple parts to this function, right? Print is kind of a unique function. It has some special syntax in it that allows it to take an arbitrary number of inputs. And what it will do is it will separate all those inputs by spaces. So we tell it to take the variable years and print it out, then take the text years is space and print that out, then seconds and print that out, and then the word seconds and print that out, right? This is where syntax highlighting is slightly useful, okay? So now I'll put in 1 year, and it's going to say that is 31 million seconds, right? That seems about right, considering that seems 60 more than however many minutes that was. There's the other thing you could have done is you could have just added another print statement that printed out the seconds, and right below our original print statement, done something along the lines of, here I'll show you, right? We could have done something along the lines of this, 1 year, and then we've got minutes and seconds. Nothing stopping you from doing that, from adding more information rather than changing. There's multiple ways to do this, and I am not pedantic enough to say that's wrong or anything like that. There might be some people, but you'll know them when you see them, right? Okay, but now let's go ahead and look at part 2, and this one's really the crux of the matter. It's a bit trickier, right? Change the problem to go in the other direction. Given the number of seconds, how many years? So let's go ahead and start flipping stuff around there, right? And then I'll leave it to you because this is a bit tricky. Because because this is math that you haven't really had to deal with since 4th grade, and this is a bit of a bigger problem than you would get in 4th grade, is the issue. So What do I mean by that? You'll see. Enter a number of years, and I'll tell you, so enter a number of seconds, and I'll tell you how many years that is, right? Okay? And so we'll change our variables around here. And don't worry about, getting rid of our stuff, because we can always rewind. Seconds is equal to this. Turn the number of seconds into a number, and we'll overwrite our text of seconds. And now we'll go ahead and kind of just like, magic over here. And then our answer will be years is equal to something. I'll put in -1 for right now. Why? Because it's a good number, right? A positive number of seconds won't be a negative. So it's just kind of a good placeholder at the moment. Years, so we're going to say seconds. Seconds is years. And this is having this kind of outline of knowing what your input is going to be and knowing kind of at least how the format of your output is going to be is useful, because you always have a quote-unquote working program, right? I can say 6,000 seconds is -1 year. That's obviously wrong, but it's a working program, right? It works in the sense that it runs. Okay. Now we have to do the magic, unfortunately, right? We have to go from seconds all the way to years. Now, when we can use some, nice braining stuff over here to help us figure this out, right? When we were going from years, from bigger units to smaller units, we were multiplying. Years to days, we were multiplying by 365. But here we're going the other way around. We are going from seconds to minutes, minutes to hours, hours to days, days to years, right? If I want to convert from days to years, right, to go from years to days, I multiplied. Here I need to divide. So we can kind of do that right here, right? Seconds. So what's the one above that? That's minutes is equal to seconds divided by 60, right? 60 seconds in a minute. Then minutes to hours. And then hours to days, right? How many hours are there in a day? 24, right? So we're going from a bigger unit and we're packing them together into a smaller unit. That's why we're dividing, right? Makes sense to everybody? We're just kind of going through in the I'll run this and then we'll compare it and we'll see how that is basically the reverse. Right? Years is equal to sorry, not days. Sorry, I messed up over here. That's the issue when you talk and you text at the same time, right? You end up saying you end up typing the wrong thing. So minutes divide by 60 to hours, hours divide by 24, that gets stored in days. Days divide by 365, and we pack that into years. That's our magic right here. And so we can say that 50 million seconds is 1.58489 years. Now remember, a year was 31 million seconds, right? That was how many we got, right? And let me just go ahead and for those of you who are frantically trying to copy this down, let me give you a bit of a help here. This is a good time to test out this feature. I'm going to hit this button. It says share code. Really? You're about to share this code with all your students. Are you sure? Yeah, I'm pretty sure. I hit the button. 164 people this got shared with. Now, if you reload this web page, this text will appear as a snapshot for you, right? So it's there for you. Okay. Now, and this is useful because I want you to have this so you can run with this because this is both very useful and very useless code. What do I mean by that? Right? Well, let's type in 50 million seconds again. 50 million seconds is 1.58548 something years. Okay? I know what a year is. This is a unit I can understand. But what the heck is a 5.585 of a year, right? I certainly don't know. That's somehow. This is not exactly a unit that humans can really understand because as I was kind of alluding to earlier, when I was complaining about the number of the number of minutes we have in an hour, right? Right, the way we measure time makes it so that this is kind of messy, right? It's hard to understand, okay, how much, a half an hour, that's what percentage of a day? It's not like a clean metric unit, right? Right? So how do we get this to be a bit easier to read? Well, the answer is that I would want something that would say, hey, this number of seconds is this many years, this many days, this many months. This many years, this many days, this many hours, right? Convert it into as big units as possible, right? It's 1 year and then whatever 0.5854 years is in days. And whatever left over for that we can't pack into days, that should be turned into hours, okay? So when we do these operations to convert from seconds all the way to years, okay, this bit, right, this is the whole number of years we want, and this bit is what's left over. You might say it's what remains. It's the remainder. This is the remainder. So here's the key here. We need to be able to capture this value somehow and use it. Now, we can, and we kind of learned about how to do this, right? Rather than using floating point division that we've been using, we're going to use fourth grade arithmetic. We're going to use quotients of whole numbers and the remainders, right? We're going to use quotients and remainders. So minutes, right, the number of minutes that this can be is, we'll take the number of 60 seconds, right? We'll take the number of seconds, divide that by 60, and it'll get us basically the number of whole minutes we can get out of however many seconds we input. And then, let's call it remaining minutes is equal to seconds. Well, this is how many are left over. Mod 60. And again, this is the part of the reason why I shared that stuff with you, because so I can make these changes very easily. Okay? And so let's go ahead and just simply see what this is if we convert it into minutes. And then, let's see. Actually, it's not remaining minutes. It's remaining seconds. It's the amount of seconds that are left over that we cannot pack into minutes, right? Is minutes, comma, and not seconds, but remaining seconds. Now, there's a reason I'm doing this, because because I'm telling you where I want to go with this, but I'm not kind of showing you the intermediate step, so I'm showing you that intermediate step. So, right, if I say, hey, let's go ahead and just switch this to minutes to a second so it matches up with reality, right? If I enter in 60, that should tell me it's 1 minute and 0 seconds, right? But if I tell you to do 90 seconds, it will tell me that is 1 minute and 30 seconds, right? Why is that? Because I have the number of seconds here, okay? I take the number of seconds, convert it convert from text to a number. Then I take that number, divide it by 60. I pack as many seconds as I can into groups of 60, and then count how many groups I have. That's the number of minutes I have. I take everything I can't pack into a minute and say, that's what I have left over. And I can't do anything else with this. It's the number of seconds. So I'll just simply print out that remaining number of seconds. And that's why we're able to say, okay, if I enter in 90 seconds, I'll pack 60 of those together. There's one group of minutes, right? And then there's 30 leftover seconds. If I do this, let's say, for 390 seconds, that's going to be 6 minutes and 30 seconds, right? It packs together 6 groups of 60 for 360, right? And then there's, again, 30 left over. I'm trying to make the math as clean as you can do in your head right now because we're not going to be able to do that really for too much longer. So with this is what we can use to build up our answer, right? We go from seconds is minutes, but in front of that we need to do hours. We got to convert the minutes to hours. But those hours are going to have leftover minutes, right? And then when we convert those hours to days, those days are going to have leftover hours, right? Right? If I ask how many days is 25 hours, then it should tell me that it is 1 day and 1 hour, right? Make sense? Right? We're not leaving so we're leaving this in human readable units, even though the code is getting less and less human readable. All right, so take about 5 minutes of this to try to get where you are. And once again, this is the way pretty much all of the lectures that we do with these kind of textbook exercises is going to work. I do the problem, I do part of the problem for you, then I tell you to take a few minutes at it, and I don't necessarily expect you to get an answer in those 5 minutes. It's a big problem. The only reason I stop is because we got other stuff to do, right? But what I'm trying to get you to do is to start thinking on this problem, to try to start figuring out how would I solve this problem. We're getting part of the way there, right? But when it comes time, I'll just simply pull it up again and get you and simply catch everybody up to the same point, right? So don't feel bad if you can't finish it in 5 minutes. I don't intend you to. I just intend you to take a crack at it. All right. I'll be going around the room and helping people if they're stuck, though. All right. So, but let's go ahead and get to this. So this one is not complicated, but it is complex because there's multiple parts, and if you mess one up, that can make it hard. But the idea is not complicated. We are just simply converting from smaller units to bigger units and storing the remainder. It's just kind of scaffolding that's the complicated part, right? Everything else after that is just simply making sure we don't mess up, right? So we've gone from seconds to minutes, and we've captured how many remaining seconds. And this kind of block of code here does tell us kind of how we want things, and I'm just going to separate it out block by block, right? Minutes, converting to minutes from seconds, and now we want to go from minutes to hours, right? So how do we convert from minutes to hours? We say, hey, there's 60 minutes in an hour. And then, right, we're going to pack as many of those minutes as possible into an hour, but it may not be possible to pack all of them. We might not have a multiple of 60. So what we're going to do is we are going to store the number of minutes we have remaining, and we're going to call that I'm going to call that rem minutes. And I use an underscore here for that. It's one of the 2 ways you can separate stuff out. It's the way Python likes to do things, by if you have a multi-word variable, putting an underscore between the words. You'll often see me do Java's version, which is this version, where you camel case it, where you separate the words by camel casing it. Why in the world is it called camel casing? A very long variable name, right? Why is that called camel casing? Because it has humps like a camel does. I know, we're terrible. If you think we're terrible at naming things, wait until you see what we call a tree in computer science. We are bad. So hours into minutes, and then we capture the remaining minutes, right? Now, whatever we do want to make sure we're consistent. Okay. Now, we need to pack those hours into the next biggest unit, which is days. So hours, not outs, hours, divided by 24 hours in a day, not 25. Okay. That gives us the amount of days, and then remaining hours is equal to, well, it's equal to hours mod 24. And remember, this is fourth grade division, integer division. This simply gives you a whole number. It doesn't care about the decimal point or anything after it. And this is the other part of fourth grade division. Just you get the remainder, right? Okay. And now from days to years. Our last step is days to years, right? There are 365 days in a year, although as we'll find out in the future, that's a lie. There are 365.25 days in a year, except that is a lie. It's actually slightly less. You'll learn that nobody actually knows how that works. So years is equal to days divided by 365. And then the number of leftover days, remainder of days, is equal to days mod 365. And it's just a matter of keeping, but it's always, but we can see here we've got our pattern, which is found on the right. It's always the same unit. Then it's just simply getting divided, then modded, divided, then modded. And then it's always the next biggest over here. So seconds is, and now we can start typing out years, comma, years, and this is going to go off the side, but whatever. Years, years, days, comma, days, hours, comma, hours, and then I've already typed the rest, which is minutes, minutes, and seconds, except it's not minutes, days, hours. That's wrong. It's day, it's years, underscore, remaining days, remaining hours, and remaining minutes. Right, the remainders that we were storing. So now if I say, hey, what is 50 million? We get, surprisingly not error, because I'm sure I would have made a mistake there. So 1 year, 213 days, 16 hours, 53 minutes, and 20 seconds. Right? Now, this is a lot of code, so I'm going to change this so seconds and how many years that is. That's a lot of code. So once again, I'm just going to run this once more to save it. Right? And I will then share it with you. Share code. There you go. It's all copied down. Now, the problem always takes a while. It's one of the 3 problems on here. That always takes a while. So this will be available to you. You know, you don't need to take a photo of it. You just have to refresh the page to see it, right? So with that said, I will move it on. So this is a bit more of a fun one, okay? So there used to be, at least for computer software engineers, this kind of particular class of not computer science questions that would get asked during interviews. They're still asked at some companies, but primarily like consulting firms and the like. And they're not necessarily useful because you generally don't get me as a professor who explains how these problems work. Okay? Which is, you get a question like, how many trees are in the state of Washington, right? Now, of course, your immediate answer is like, this is now a silly question because I can just ask AI, right? Or something, but how do we even make this estimate? All right, another one I've often heard is like, how many houses could fit in the Empire State Building, right? That's another one, or how heavy is the Empire State Building, which ends up being the same kind of question. These are kind of questions where the answer really doesn't matter, though, because even if I ask AI, it's going to give me wildly different responses, because The answer is nobody freaking knows because nobody's actually gone and done a physical census of all the trees. You don't count them all because, as you'll soon find out, there's too freaking many of them. Okay? Similarly, how much does that work? I'm sorry, does that hold? The Empire State Building hold? It's tricky. There's another one that's like this called, there's one that was posted similar to this on the blog for XKCD called What If? So if you don't know about XKCD, I highly recommend it, XKCD, just so you know. XKCD is a webcomic about just random math and science stuff a lot of the time. And there's some very, very, very good comics with some nice inside jokes about, and some of them do need explaining. And there's an entire wiki dedicated to explaining the concepts that are in them. But he also runs a blog called What If, which is serious answers to absurd questions and absurd advice for common concerns. So some other questions on What If are comet ice. If I cool down the Earth by capturing a comet and dropping it into the ocean, could I cool down the Earth by capturing a comet and dropping it into the ocean like an ice cube in a glass of water? Right? Star ownership, transatlantic car rental, hailstones. How much damage would a hailstorm with a size 3 soccer ball-sized hail do? So he answers these kind of questions. I heard bananas are radioactive. If they are radioactive, then they radiate energy. How many bananas would you need to power a house? The answer is yes, that's true, but you need to eat millions upon millions of bananas to equal even a single X-ray, right? It's kind of absurd. Everything's radioactive. It's fine. So the question here is that a good one is Google's data centers on PunchCard, and this is like from the 2010s, but the calculation still holds even if the numbers no longer do, right? So PunchCards used to be the way that some computer programs are stored long before I was a professor. I'm not that old. So these basically don't hold that much, and we'll find out. Now, Google probably has more data storage, at least at that point, than any other place on any other organization on Earth. There are some other orgs that might have more, as he says. The NSA, right? We all know about the NSA, National Security Agency. We all know about the CIA. But NRO? NGIP? I mean, how many of you know about the NRO? No, of course not. Even though it's one of our spy agencies, why the heck would you know about it? We've got a lot of them. NRO was only declassified in the 90s anyway. Above and beyond. Great motto, by the way, for your field. National Reconnaissance Office. Let's go ahead and check out what they are on Wikipedia. NRO Wiki. Okay, just so NRO is an intelligence community and agency of the DoD which designs, builds, launches, and operates reconnaissance satellites. So of course that would require a lot of data. Have you seen how much data Google Maps needs? Right? Except this is, for probably a bit more exciting purposes than just simply getting to the grocery store. So there are some groups like that. NGIP. Let's see. Oh, .mil. Yeah, that's military, right? So that's a fairly straightforward kind of idea over there, but very similar. Amazon, Facebook, and Microsoft also have tons of servers and stuff like that, so very comparable for the Googles these days. So the question is, how many data centers do they have, right? Because we're trying to convert the number of, how big is their thing, to punch cards. How in the world do we do that? Well, first we got to figure out how many data centers they have. And once we figure out how many data centers we have from Google, we might be able to say how many computers live in a data center. And then when we turn it into how many computers, we can do this entire conversion process we've been doing. Go from data centers to computers to amount of storage a computer holds to converting that storage into punch cards. Okay. So, again, this is back from the 2010s. Look at the amount of money they have, right? Biggest data centers cost about $500 million to $1 billion. Can't have more than 20. And so that they acknowledge they have data centers in these 13 locations. And they might have other ones. Note that Atlanta, Georgia occurs twice. That's interesting, ain't it? There's a lot of power, a lot of conduit, let's say, goes through Atlanta. So a good kind of rule of thumb here is like, this becomes harder and harder. So the question is maybe by measuring the amount of energy that they use. And that's actually pretty good because they tell you. The company disclosed in 2010 that they consumed on average 258 megawatts of power. That's 258 million watts of power. So how many computers can you run with that? And so he does some quick ballpark calculation based on the fact that he plays with computers a lot, and that's 215 watts per computer. So do some division, about 1 million servers. Then the question is, how much do those have? 2 terabytes is probably a good amount for each server at that time. And so 10 exabytes. And then he says, okay, we go from 10 exabytes. And, right, so how do we do this? So there's this many bytes, so that's this many bytes. A punch card can hold 80 characters, and a box of cards holds 2,000 characters. So 15 exabytes of punch card would be enough to cover my home region, New England, to a depth of 4.5 kilometers. That's about 3 times deeper than the ice sheets that covered the region during the last advance of the glaciers. Punch cards, ice sheets, Boston. So yes, absurd questions like this. It's a lot of fun to figure that out. He then mentions, like, as far as figuring out where these data centers are, you know, there's a number of undisclosed or like discrete sites that Google, you know, because Google isn't necessarily going to put a big sign, Google here, for all their data centers, right? Same with Microsoft or anywhere else. So how do you know where they are? Pizza delivery guys. In fact, there's a Twitter account, probably one on Blue Sky or whatever feed we use these days, right? There's one that specifically tracks the activity of Domino's and Papa John's and other pizza places by the Pentagon, because when those get really exciting in the night, you know some major news is going to break because they're ordering in pizza. Well, they're not ordering in pizza because they have stuff, then the security clearance, but everybody around it who's in the know knows about it, and they're ordering in pizza because they need food. Anyway, it's seriously, check it out. It's fun stuff. All right, so going back to that, how many trees are in the state of Washington? Let's go ahead and open up an incognito window for a second, mainly because I'm just not ready to dox my home address on, on YouTube. So we're going to go to maps.google. May have done that anyway. Let's see right now. Okay. So, well, fortunately, that's what editing is for. Let's go to over here to the state of Washington. So when we were talking about Washington to everybody who's not a U.S. citizen, we were not talking about this. That's the District of Columbia. This is the state of Washington. How many trees are in the state of Washington? Now, we actually kind of get a good idea right over here. First off, this is Washington. Let's click on it to kind of highlight the borders, right? And let's go ahead and go to a satellite layer for a second, right? So, how much would you say, approximately speaking, and I'm only looking for an approximation, how much of that is tree? Right? How much of that state is tree? Like 2/3? At least half? Yeah, I'd go with half. I'd go with anywhere, I think anywhere from saying half to 2/3 is tree is a fairly good guess. Also, notice what's going on over here with the borders of Washington. Point Roberts, right? All these borders are all sorts of fun, right? International borders. Almost as if, though, they're completely arbitrary things, right? They're not. They're very, very not, but at the same time they are. So, anyway, we've got our borders. Now, we've got about half of this being tree. Let's go ahead and say that if it's essentially, let's go ahead and simplify our assumptions here. We're going to assume that even though this totally does have tree in it, it doesn't have any tree in it, right? We're just going to simplify our assumption. This area, with all the nice water and stuff, obviously no trees live there. We know that's a lie, right? We can zoom in and probably find some trees somewhere. I mean, somewhere. I guess that's not important enough to tell. We know that, like, in cities, they'll plant trees as well, right? Okay. Right, so if I went to, I'm running out of time here. I'm not going to play around with that. Point being is that we can assume this is all not tree and just assume that the forests have the trees. So the question is, how many trees are in a unit of forest? What in the world is a unit of forest? So with those questions in mind, take 5 minutes and try to figure this out. There is a window over here for you to do that calculation, right? So try to figure that out. Given how big, so things I would look up. How big is the state of Washington? How much tree is in the state of Washington? Okay. Pause. Too long. I think for the last part of that. All right. So we did that bit. So again, for our triangular numbers, okay, let's go ahead and look. Sorry, our triangular numbers always follow the pattern of answering this equation. What is this sum? 1 plus 2 plus 3 plus 4 plus 5, dot, 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 all the way to some value. This is what we're trying to answer, right? Notice that that's what's going on here. We added with one person, then 2 people, then 3 people, then 4 people, then 5 people, then 6 people. We added a 6th person, so we added 5 more handshakes, right? Let's go ahead and look at this. How many handshakes got added? 1 handshake, 2 handshakes, 3 handshakes, 4 handshakes, 5 handshakes got added, right? 1 plus 2 plus 3 plus 4 plus 5. So, basically, if we're trying to figure out how many handshakes 150 people had, we'd set n equal to 49 in here and ask 1 plus 2 plus 3 plus 4. Now, mind you, doing that on a computer is actually not that hard once you learn how to do for loops. But there's, fortunately for us, a fairly straightforward equation for this. And if you take Calc 2, you will learn this equation because guaranteed it will be on an exam as a proof. N times n plus 1 over 2. I've had to do this enough times I had it memorized. Those two things are equal somehow, and it's actually the assignment in Calculus 2 to actually have to prove them. For those of you who don't have to take Calc 2, rejoice, because you can just simply look it up. But for here, we can see, hey, 1 plus 2 plus, we can check this for 5. 1 plus 2 plus 3 plus 4 plus 5, right? We have 9, 12, 13, 14, 15. Now let's check the other side of the equation. 5 plus, so we have 5 over here. We have 5 plus 1, which is 6. 5 times 6 is 30. Divide by 2, that's 15, right? Math checks out, right? Obviously, though, if we were proving it actually proving it, we couldn't just simply plug in numbers and check because that's not thorough enough. But it gives us enough that we can probably just plug this in. Assume 150 people. There are 149, there are, assume 159 people. Use. Handshakes. Okay, and now, so we can print that out fairly straightforward and say 149 times 149 plus 1, which is 150, divided by 2, and it's going to be a whole number anyway, so might as well. And so if there were 150 people in this class, then there would be a grand total of 11,175 handshakes that would occur. All right. Again, I would have probably worked on making that as much as possible for people to just try to see, but we've been running out of time, and it's 3:17. So class is dismissed. I will mention that you will want to watch the next video on Module 3. And on Tuesday, we will do more drawing with turtles. So, and that will accompany what Lab 3 is, which is drawing with turtles. Hi there.
For the past 2 days, I wasn't able to complete the textbook assignments.
Okay.
Is that okay? Because I just...
Textbook assignments, I don't care when they get done, as long as they get done.
All right. So that doesn't matter.
There's no late penalty for the
All
textbook.
right. Thank you so much. Yeah, I'm having some issues, and anything I have, I'll try to email you right
Yeah.
away.
All right, take care. Just plug something in. It's fine. Okay. There wasn't really code so much as you were kind of jotting down notes as you went down. That's the idea. Okay. You can. You can also demo it in your lab. The way it works is that, yes, I can take demos after class, but I handle questions first. So does anybody have questions that aren't demos before I start doing demos? Yes, no? Questions before demos. Does anybody have questions? Mm-hmm.
How much, am I supposed to understand all this right away? Everything else stuff there?
Define everything. This part, the lecture got harder and harder as it went on, so that's fine. The most important part is understanding the first exercise.
This right here?
If you understood that, then you're in great shape.
Okay.
If you understood part of that, then, rewatch the recording and try to follow along for the conversion. Because the problem in your homework is to convert from seconds to hours. And it follows pretty much the exact same pattern. It follows, not pretty much, it follows the exact same pattern.
Okay. And then for the homework, this would it be the homework, right?
This is just an in-class exercise. So it's just simply, all you have to do is make sure that this bar gets filled up by interacting with all the interactables.
Okay, copy.
Okay.
And then the assignments I should find here, right?
The assignment, so let me go ahead and show you, okay? So, we got over here, in general, so if I assume, I went to the person icon and clicked on assignments. So these are your readings. I'm not just now able to do that. That's fine. It's fine. Yeah, I'm not, you're not being held. These textbook exercises are soft, meaning that as long as they get done, they get graded at full credit. Okay. These are basically the reward for keeping on top of the material. Okay. These are all. This is for the entire semester. This is everything, and these are the due dates for that. If you can get done to these due dates, great. If not, get done what you can. Okay. These between the textbook. Between this and what we do in class, that's 15% of the grade. 25% of the grade is your classical assignments. Let's go to modules. Modules get you better over the assignments. Your lab 1, lab 2, these are much closer to your assignment, homework. Okay. So these are done in lab and at home, right? Or you get them started in lab, you work on them at home, you ask help on them. But basically, you get a 2-hour block of time to work on that aspect. They have to be shown to your TA or to you to get credit. Okay. That's what makes them. But these are, you can basically, this is out like this. You've got a week to work on these. These things, if you spend more, you get the exercises chosen out of the textbook. right? If you're spending more than 15 minutes on one, then something's gone horribly wrong and you should okay. So that's the point. These are meant to be quick, nice, quick checks. How you getting this?
So it's going to be those.
Yeah, I would work on these before working on the labs.
So basically, I go.
Yep. Sorry. Once we get to the latter end of the semester, you're not going to be working on any of that anymore. Instead, transition.
I was in class and I just responded to Brendan. So please. And since you have that slot between classes, so you should be fine taking the quiz in between. Rather than having something Friday. So that's why I said tomorrow. Yeah, very good. Great. I know what time it is. I mentioned 11. Someone mentioned 11. Did he say? I put 11. No, can you like schedule it as early as possible? So the sooner.
So I can do that for the next test whenever that is. I just have to know like 3 days ahead of time so that I can use it.
So, and if you still have questions after that,
I announcement like
which I should do this weekend, I'm hoping to do this weekend. Then you can just simply reach out.
Now I know I'm gonna have to get it for as soon as possible.
There, Tuesday and Thursday, we will walk things out. 12:30 to 1:30. However, if you want specific help, or just in general help, you email me. We'll find a time to meet on Zoom. Okay, so I'm available to meet tomorrow and all that stuff. Or I can meet Saturday evening or sometimes Sunday. I'm available.
Yeah, I'll be on.
Demos, right? Okay, so we are going to, here's what we're going to do. We are going to move.
Sorry, I started setting up.
That's what you should do.
Thank you.
We are going to move out of the calculus, right?
Yeah.
Yeah. Yeah, it was. I briefly